Example number 7. A rifle accelerates 12-gram bullets from rest to 250 meters per second. The rifle barrel is about 0.85 meters long. Find the impulse acting on the bullet and the force on the bullet. Alright, so what's going on here? Say we have a big long rifle. Maybe you can draw a better rifle than I can. And the bullets start out at this end of the rifle, and they get accelerated as they go along the barrel, which is supposed to be 0.85 meters long. Pretty long barrel. And we want to figure out, well, what would cause that? What would be the impulse on the bullet, and what would be the force on the bullet? So we have a mass of 12 grams, which you need to convert into kilograms. 1,000 grams is 1 kilogram, so this is going to end up being 0.012 kilos. Put us in base units. From rest, that's my V initial, 0 meters per second, to 250 meters per second, V final. And that 8.85 meters, that's going to be the distance that it happens over. May or may not need that right away, we'll see. We're looking for the impulse, so remember that's the change in momentum, and we're looking at the force. So probably if I find the impulse, that's going to let me find the force. We'll see how that goes. So impulse is mass times change in velocity. I can actually figure that out right away. So my mass 0.012 times my V final minus my V initial, and that is 0.012 times 250. Gives me an impulse of, wow, just 3.0. Let's put that in kilograms, meters per second. Okay, so that one was just one step. There was no extra work there, so the next one must be a little trickier then. If I want to find the force, I know that impulse is force times time, but I don't have the time given in this scenario. So that must mean I can find the time using another method. And in this case, the method I'm going to need to find time is going to be kinematics. So pull out your kinematics equations, and I find one that says displacement or distance equals V final plus V initial over 2 times time, something like that. This is the average velocity, V final plus V initial, or you could do it the other way around, V initial plus V final, because it's positive, doesn't matter which way you go. Divide by 2. That's going to give me my average velocity. So if I want to solve that for time, multiply the 2 up to the other side and divide by this quantity here. So I'm going to get time is 2d over V final plus V initial. That's going to be my time. So I can plug in the information that I have, my 0.85 for distance. My final velocity is 250 plus 0 is just going to be 250, and type that in. And my calculator tells me that's actually a very small number of 6.8 times 10 to the minus 3 seconds. But using that very small number, now that I have it, I can solve this for the force. So force is change in momentum over time. So my change in momentum was 3, and my time was 6.8 times 10 to the minus 3. Make sure you're using that exponential button on your calculator to type that in so you don't mess up. 6.8 e minus 3. And that gives me a force of 441 newtons. Was there a direction given in the question? No, no direction? Then that is it, and I am done. Sweet. So as you can see, we keep pulling in kinematics in different ways. Hopefully you're comfortable with your kinematics equations and you can use them to solve for things like time and V final that end up being useful in our impulse equations. Example number 8. Consider the diagram to the right for the next 3 questions. So I have a car with initial velocity of 5 meters per second, hits the wall and bounces off at 4 meters per second in the other direction. My case B, I have a car with 5 meters per second, hits the wall, comes to a stop. That one's probably more likely unless you happen to have a rubber car. The diagram depicts initial and final velocities of an 800 kilogram car in 2 different collisions with a wall. In case A, the car rebounds upon collision. In case B, the car hits the wall, crumples up, and stops. Assume that the collision time for each collision is the same, so same amount of time. In which case does the car experience the greatest momentum change? Well, we could actually calculate that in both cases. Change in momentum, we know, is going to be mv final minus mv initial. And in both cases, my mv initial is the same. So this part isn't going to change anything in terms of my momentum change. I could use my 800 kilograms. This is going to be 800 here. And in one case, so this 5 is positive because it's going to the right, it's going to the east, whatever you like. This is plus 5, and this is going to be a minus 4 or 0. So this is going to be either 800 times minus 4 or 800 times 0, and this is always going to be 800 times 5. So in either case, we're going to have a negative change in momentum. It's either going to be 800 times minus 4 or 800 times 0, whichever you like. So if you want to crunch the numbers, you'll find that the greatest negative momentum is actually going to be the one where you bounce off. It was going at 5 meters per second, then was going at 4 meters per second. In the opposite direction is a change of 9 meters per second. 5 minus 4, or minus 4 minus 5. In the case where we come to a stop, 0 minus 5 is just going to be a change of negative 5 for velocity, which is going to be a smaller change in momentum. So case A has a bigger momentum change in momentum. Question number 2, in which case does the car experience the greatest impulse? Well, impulse is the same thing as the change in momentum or momentum change. So car A has the greatest momentum change, then car A experiences the greater impulse. The impulse encountered by the 800 kilogram car in case A has a magnitude of blank Newton seconds. So actually we can go ahead and crunch these numbers. 800 times negative 4 minus 800 times 5. And I've got negative 720 Newton seconds. Now they just left off the negative because they're given the magnitude, they're ignoring the direction. Remember that the negative is really only helpful for finding direction. So that's the answer that I'm looking for. Sweet!